So, what if the single biggest threat to your Node.js application wasn't actually in your JavaScript code? Today, we're going to pull back the curtain on a hidden layer of Node.js. We're talking about a C++ engine that, when you ignore it, can bring even the most stable production systems to a grinding, painful halt.
And this quote right here, it just nails it. It gets to the very heart of a super mysterious production failure that had an entire, very smart engineering team completely stumped. They thought they knew Node.js inside and out, but it turns out they were looking in a completely different universe.
All right, let's get into the anatomy of this failure because it's a fascinating story. It all starts with what seems like a totally simple image upload service. I mean, this thing passed every test, aced staging, everything looked perfect. But the second it hit real production traffic, it all started to fall apart, catastrophically. Now, the symptoms themselves were just bizarre. You'd have requests that would just randomly hang for a full 10 seconds. The CPU would do nothing, just sit at 0%, and then bam, suddenly spike to 100% on a single core. And the logs? A ghost town. You could see a request come in and then nothing. It was like it vanished into a black hole, only to pop back out seconds later, totally fine, with zero explanation.
So for 3 agonizing days, the team was completely lost. I mean, they threw everything they had at this thing, profiling tools, extra logging, endless code reviews, and they found absolutely nothing. The big breakthrough only happened when they decided to go a layer deeper, using a system tool called strace to actually peek under the hood of Node itself.
So where do they even start looking? Well, naturally, they assumed the bug had to be in their own application code. They spent days chasing ghosts in the JavaScript layer.
They went down the entire checklist of the usual suspects, Could it be an unresolved promise hanging out there? Nope. Maybe some accidental blocking code? They checked. Nothing. Is the event loop blocked? Is the garbage collector going crazy? Is it a slow database? Every single theory they had just led to a dead end.
And that's when their analysis led them to this really startling, kind of uncomfortable conclusion. Their JavaScript code was fine. The failure wasn't in their code at all. It was happening somewhere deeper, inside the Node.js runtime itself.
It turns out the real culprit was hiding in plain sight the whole time, in the C++ engine room of Node.js that most of us JavaScript developers just completely overlook, and it has a name, Libuv.
Okay, to really get what went wrong here, we have to correct a huge misconception. Node.js is not just a JavaScript runtime. It's a JavaScript runtime, the V8 engine, that's literally built on top of a super powerful C++ I/O runtime, which is Libuv. And that distinction, well, that's everything.
Now here's where it gets really interesting. Inside the C++ layer, Libuv, not all async work is treated the same way. Some stuff, like network I/O, is handled right on the main event loop, and it's truly non-blocking. But, and this is a big but, other tasks like file system access, DNS lookups, and crucially, some crypto functions get offloaded to a completely separate C++ thread pool.
And here it is, the bottleneck. A single number, 4. By default, that entire C++ thread pool that handles all this important work has a maximum size of just 4. Think about that. Only 4 threads to handle every single file read, every DNS lookup, and every crypto operation for your entire application.
And let's be super clear here. This thread pool isn't some JavaScript feature you can tweak easily. It's managed by Libuv, a C library that is the absolute bedrock for all of Node's asynchronous I/O capabilities.
And just like that, the mystery was solved. You have dozens of simultaneous image uploads, all hitting functions from the crypto module. Every single one of those calls was a new job being sent to that tiny 4-thread pool. The pool was instantly saturated, and all the new requests just started queuing up, stuck, waiting for one of those 4 precious threads to become free.
So, okay, they found the problem. Awesome. But now, how do you actually fix it?
Well, like with most real-world engineering problems, there wasn't one single right answer. They had to weigh the pros and cons of 3 very different approaches.
So these are the trade-offs they were staring at. Option 1, just increase the thread pool size. It's simple, it's a one-line fix, but it's really just treating the symptom, not the root cause. Option 2, move all that crypto work to a background queue. Now that's a really robust solution, but it adds a ton of new architectural complexity. Or option 3, just get rid of the native crypto module entirely and use something else, but that means making some tough trades between performance and resource isolation.
And this, right here, might be the single most important lesson from this whole story. You cannot solve a low-level, hardware-level constraint with high-level syntax.
Wrapping more and more calls in async await doesn't magically create more C++ threads. All it does is create a longer and longer line of tasks waiting for threads that simply are not there.
You know, this whole incident, as painful as it was, forced the entire team to adopt a much more sophisticated mental model for how they build Node.js systems. It's a model that actually respects the C++ layer that's humming away right underneath their JavaScript.
So the key takeaway, the big mental shift you need to make, is to stop thinking of Node.js as just JavaScript. The correct way to see it is as a layered system. You have your JavaScript application code running on top of this powerful C++ runtime that has its own very distinct and very real resource pools and limitations. So how do you put this into practice? How do you avoid this kind of disaster in your own apps? Well, it's 3 steps. First, classify your workloads. Know exactly which operations in your code are going to hit that thread pool. Second, you have to monitor the runtime layer itself. That means tracking not just event loop lag, but thread pool saturation. And finally, you have to design your entire system around these constraints, knowing that this thread pool is a primary bottleneck.
And look, if you think this is just some minor technical detail, just look at the business impact. 3 full days of engineering time just gone. A terrible experience for users, and a near miss on a major product launch. All of that pain because of a misunderstanding that was ultimately fixed with a single line of configuration. This isn't just a tech curiosity, it's a real financial and product risk.
Ultimately, this whole story leaves us with a pretty provocative question that I think every developer should ask themselves. You know your JavaScript code, you're an expert in it, but do you have any idea what's really executing it? Because as we've just seen, your entire production stability could depend on the answer.